Okay, so the last thing we have is projectile motion. And that will take us today, Monday and Tuesday, review on Wednesday, and then the, what's this with this here? And then the written final will be on Thursday. Written final is all multiple choice, okay? So we'll deal with, and projectile motion is just going to be included on that. I'm not going to have a separate test over projectile motion. So the beauty of projectile motion is that we don't have to learn any new equations. We just have to apply them to a new situation. So with projectile motion, there's two generic types of motion. The first one is what we call a lemming problem, where an object is just shot off of a table, a car drives off a cliff, something like that. And the only motion that you have is Vx. And the reason that I call it a lemming problem is that there's a small kind of rodent-looking animal that lives in England, and lemmings are known for like jumping off of a cliff, okay, off the cliffs of Dover. And so when someone says, hey, don't be a lemming, what they're saying is that, hey, don't follow everybody else off the cliff, because these lemmings would run to the edge, and they'd jump off the cliff, and they would drown in the ocean. So if you've never heard of a lemming, that's what I'm referring to when I call it a lemming problem. Then the other one would be like a golf ball shot, where something goes up and then comes back down. So oddly enough, there's going to be gravity involved. Oddly enough, there's going to be acceleration involved. Oddly enough, we're going to be talking about velocity time graphs. And literally, there's just no new equations. We just have to repackage them. Okay, so here's going to be what's similar, and here's what's going to be different between these two problems. Today we're just going to deal with projectile, with the lemming problems over here. So the biggest thing with the lemming problem is that it has no initial velocity. So the other thing that's going to be a little bit different is that up to this point we've dealt with horizontal motion and we dealt with vertical motion. Okay, like I take this and I throw it up in the air and I go, oh, here's my initial velocity, find the maximum height, all this good stuff. Or I roll it along the ground, it has some initial velocity, and then we make it stop. So what's unique about lemming problems is that now we're going to combine them together. So now we're going to combine horizontal motion with vertical motion all at the same time. But here's your other mantra. Just like if you remember, if you've ever seen the ads for Vegas, what's the theme for the ads in Vegas? What happens in Vegas stays in Vegas, okay? We're going to do a similar type thing, okay, without the gambling. So we're going to say what happens in the X stays in the X. So what happens in horizontal motion stays in the horizontal. What happens in the vertical stays in the vertical. They can combine in terms of like, oh, I have a horizontal velocity and then I have a vertical velocity and then I can find the resultant. But here's your mantra when it comes to projectile motion. What happens in the X stays in the X. What happens in the Y stays in the Y. Okay, that's it. So when I talk about this VYO, okay, VY9, what I'm talking about is the initial vertical velocity. Okay, so what that means is if I just drop this thing straight down, or if I throw it horizontally, in both situations, my initial vertical velocity is going to be 0. Okay, so whether I drop it, whether I throw it, doesn't make any difference. My initial vertical velocity is 0. So what happens in the Y stays in the Y. So because of the fact that we're in a gravitational field, as soon as it leaves this table, or I throw it or whatever, it's going to begin to accelerate, okay? Because we have the only imbalanced force that we have, and this is why you learn forces before you learn about projectile motion. Because as soon as this thing goes in the air, oh, the only force acting on it is gravity. Since the only force acting on it is gravity, that means the only acceleration I'm going to have is pointing straight down, which is going to have a value of 9.8 meters per second squared. Okay, nothing new there. But the other key assumption we're going to make about Vx is that we're going to assume that Vx is constant, okay? So what we're going to assume is that when whatever launch velocity you have in the horizontal direction stays there. Now, the only way that can happen is if there are no forces acting in the x direction. So what we're going to assume is that there is no forces acting in the x direction. So this is like that limb lab. You know, when we said, hey, you know, on the moon and you fire your side engines, that's the only time you accelerate because that's the only time there's horizontal forces. Same thing we're going to happen here. So because of the fact that we're going to assume that the horizontal velocity is constant, which makes life so much simpler, we're going to use a fancy looking equation that says range equals Vx time, okay? So that's your range, that's your horizontal velocity, and then you're going to have time. So range is how far it goes, okay? So one of the things you're going to do in a lab today, you're going to take a ramp like this, and you're going to roll a marble down. Oh! I want to put up a sign that says just do not disturb. Thank you. Whoa.
Got caught on your desk.
I was like, whoa, don't take my desk. Okay. So range is going to be how far it's going to go. So what you're going to do is you're going to measure, you're going to roll a marble down this ramp, and you're going to measure how far it falls before it hits the ground. Okay? So horizontal distance is what we're going to call range. So the only time we can use this, velocity times time, which is a fancy way of saying D equals VT, right? Y'all have done this before. Remember, the only time you can use that is when the velocity is constant. So we're going to make the horizontal motion simple. Now, in reality, this isn't true. Okay? It's so not true, especially in Kansas, if you've ever played outdoor sports, and especially in the wind, okay? Like if you've played soccer or if you kick the ball and it's a strong south wind and you kick it with the wind, that ball is going to go forever, okay? But in the opposite, if you try and kick that ball into the wind, it's going to knock it down, okay? Softball, whatever outdoor sport it is, okay? In reality, depending upon the wind, this statement is not true. But that's just going to really complicate things because then you have to have like the drag coefficient. Softballs have different drag coefficient than soccer balls do, than footballs do, and you'd have to know the wind speed and humidity, and it's a very, very complicated calculation to actually determine what that drag coefficient is, and then what's the acceleration and all that good stuff. And we said, too complicated. Screw it. We're just going to assume that Vx is constant. In reality, it's not, but we're just going to make it that way. But it's a pretty good, usually there isn't that much deviation. Okay. So the other thing that's going to happen is that because of the fact that there are no forces acting in the x direction, inertia is the dominant thing. So when I roll that ball off, it has a certain amount of mass, it has a certain inertia, it wants to maintain a constant velocity. So what we're saying is that there is no horizontal mafia. When that ball rolls off or you hit a golf ball in the air, we're assuming that the only mafia that has any influence at all is the gravity mafia. We're assuming that the frictional mafia doesn't impact the flight of a ball. Okay? So we're just saying, hey boys, sorry, you all don't get to vote. Gravity mafia, yeah, you kind of get to vote because you're there. Horizontal mafia, not part of the story, okay, which makes life simpler. So what that means is if you were to draw a velocity time graph for horizontal motion, that's just going to stay the same, okay? That's just going to stay at 5 meters per second, 10 meters per second, whatever that is. So if you know the time, and this harkens back to, this is kind of a nice review from the final as well, is that what we're assuming is that that velocity stays constant. Oh, there's no acceleration. Oh, it's a horizontal line. If I find the area underneath that graph, oh, that's my displacement. Okay? So this whole thing kind of ties in. You go, oh, right, no forces, right, no acceleration, right. Velocity time graph, horizontal line. Find the area underneath it, that's a rectangle, boom, I get my displacement. So, what we're going to look at is I'll use a ballpoint one. Okay. Now I'll use my baseball. Yeah, baseball. Okay, so I got a baseball. So for now, I want you to all to pretend that you don't know anything about projectile motion. So pretend that what I just talked about, erase that from your minds temporarily. Okay? Temporarily. I want to take a baseball and I'm going to hold that up to a height of 2 meters. Okay? So like this. And I'm going to drop the baseball. Okay? So it's pretend that you all are getting ready for the acceleration test. Okay? So imagine this is a couple weeks ago, all getting ready for the acceleration test. I'm going to hold the baseball up, height of 2 meters, and I'm going to drop it. So Connor, what are some things that I can find if I know I'm going to drop a ball from a height of 2 meters? What are some things that I can determine when it hits the ground?
Velocity.
I can figure out how fast it's going. Okay? What else can I find?
Displacement.
I got that. 2 meters.
Time.
I can find time. Okay? Those are the big ones. Okay? I can figure out how fast it's going. I can figure out how long it's in the air. Now, because I'm going to drop it, my initial velocity is 0. Okay, that makes life simple, right? So, which one do you Jaden, which one do you want to do first, velocity or time?
Velocity.
Okay, so I don't know time. I don't know time. So how can I find velocity without knowing time? That equation, okay? So I got v squared equals v naught squared plus 2ad. Okay, that equation. My initial velocity is 0. V equals the square root. Somebody get out a calculator. 2ad. Okay. So I'm going to take 2 times negative 9.8 meters per second squared. Down is defined as negative. That's a negative 2 meters. So that way I don't have negative signs underneath the radical. That's awkward. Then you have imaginary velocities. Doesn't end well. So somebody crunch some numbers.
I got 6.26.
Fantastic. Okay? 6.26 meters per second. Okay? So that's how long it's going when it hits the ground. So right away, now let's talk about time. Before we do the calculations of time, is my time going to be bigger or smaller than 1 second since the ball was only going 6.26 meters per second when it hit the ground? Is my time going to be more than a second or less than a second? Why?
Because it takes 6.26 for 1, or 6.26 meters for 1 second, and you only want 2 meters.
No. Think about this. Let me rephrase what you said. You're looking, I want to change your perspective a little bit. What's my acceleration?
6.2.
No. What's my acceleration? Negative 9.8 meters per second per second, right?
Mm-hmm.
So if the ball fell for 1 second, how fast would it be going? If the ball fell for exactly 1 second, how fast would it be going when it hits the ground?
6.2.
No.
Wait, which one?
Okay. If I drop the ball, and let's say it actually fell for 1 second with an acceleration of 9.8 meters per second squared. So if the ball fell for 1 second with an acceleration of 9.8 meters per second squared, how fast would the ball be going? 9.8 meters per second. So since I'm going less than 9.8 meters per second, my time has to be less than 1 second. Okay, so look at it from time, not distance. Okay? So I know my time has to be less than 1 second, right? So embrace this. Distance equals 1/2 at squared plus v naught time. Okay? I drop it. What's my initial velocity? 0. That whole thing goes away, right? 2d divided by a, the square root of that gets me time. This should be old hat. You should be able to look at that and go, Burkham, got this, cool. Okay, here we go. So that's going to be 2 times, technically, a negative 2 meters divided by negative 9.8 meters per second squared. So otherwise known as 4 divided by 9.8, and then the square root of that gives me what? 0 point something.
.639.
0.639 seconds. Okay? Boom, there you go. Now, which matches? We said the time should be less than a second. It is. Okay? Because we weren't going 9.8 meters per second when we hit the ground. Okay? 0.639 seconds. Less than a second. Makes sense. Now, the other thing that you need to begin to look at, and this as you get into more complicated math and science, no matter no matter where you go with this, even if you study economics, you need to look at what is a factor and what is not a factor. Okay? So, the fact that I dropped a baseball, is that the fact that I dropped a baseball have any influence on those calculations? In other words, would those calculations have been different if I had dropped a piece of plastic? Would that have changed anything? Same answer, right? Did you have to have the mass of the baseball? Don't need it, right? Whether I drop this piece of plastic, whether I drop a baseball, whether I drop paint. Everything's going to accelerate at the same rate, okay? As long as the only influence on it is gravity. So you have to look at what's a factor and what is not a factor. So here's what I want you to see. There are only two things, and two things only, that determine how fast something is going when it hits the ground and how long it's in the air. You have two things, and they're common to both. It's how far it's going to fall and the acceleration due to gravity. That's it. Those are the only two things. As long as I just drop something, as long as I just drop it, and my initial velocity is 0, there are only two variables that play a part. The rate at which the velocity changes and how far it falls. That influences my velocity, and I have those same two variables that influence my time. That's it. Okay? That is it. Nothing else. How far it falls and the acceleration due to gravity. That's it. The mass doesn't matter. The fact that it's got some scuffs on it and it's a white baseball, not part of the story. Okay? Can't factor that in. Not part of the story. Two things. Distance, acceleration. That's it. Okay. Now, we're going to play the what if game. So, we're going to look at time again, and we're going to look at velocity again. So let's deal with velocity first, because that's what we did the first time. We said velocity equals square root of 2AD. So when I did that the first time, I got a velocity of 6.26 meters per second. Okay, with height of 2 meters. Now I'm going to double the height. Okay, I'm going to double the height. So now I'm going to double the height, and I'm going to make it 4 meters. Okay, I'd have to crawl it through the ceiling to get to that. My ceiling's about 2.5 meters tall. Okay, so I'm going to go all the way up to 4 meters. So here's my question. Jack, I'm going to double the height. Do you think my velocity is going to double, since it's going to fall twice as far? It's funny, without my glasses, all I see is this plaid flannel blend in the back corner. Just like one big blur. Okay, anyway, Jack, is my velocity going to double?
No, not quite.
Why? You're right, it's not.
Because you don't just double the distance.
Sure I do.
Well, you double the distance, but...
What do you mean I take double this? Sure I do. 2 times 2 is 4. There's no other way around that, okay?
But then you have the square root.
Oh! That's your reaction, okay? It's underneath the radical, okay? It's underneath the radical. So I want to show you 2 ways that you can think this through. One option is that you do smash mouth physics. It's like Burkamp, I hate this whole variable thing, it just flips me out. Okay, sorry. So your other option is that you can just do this. You can take 2 times negative 9.8 meters per second squared times 4 meters. Okay, and you can do that. It's like, Brookhamp, I hate the whole variable thing. I'm a numbers kind of person. Fine, do the numbers. So, somebody do this. Take 8 times 9.8 and the square root of that. What do you get?
It's 8.85.
8.85 meters per second, which is nowhere near close to doubling the velocity. Because if I doubled the velocity, I'd be like at 12.6. Okay, so this in no way is anywhere close to doubling it. Is it faster? Yeah. Is it doubled? No. Okay. So if you're into smash mouth physics, you can do that. Now here's your other option, and this is the more elegant approach. It actually makes it simpler. If you look at this being my initial, this is how I find my initial velocity, square root of 2AD. It's cool, right? Now, to find the new velocity, I'm going to call this V prime. Okay, that's going to be my new velocity. That's going to be the square root of 2 times A times 2D. Because fundamentally, that's what I did, is I doubled it. Okay, so that would be 2D. So we're going to do a little bit of hocus pocus, and we can rewrite that as the square root of 2 times 2AD. So all I did was that I took that 2 from underneath the radical, and I kept it underneath the radical. Now, out of curiosity, Izzy, do me a favor. Take the square root of 2 and multiply that by that initial velocity of 6.26. So take the square root of 2 times 6.26. You get the exact same answer. Okay? So if you're into smash mouth physics, put in 4 meters, calculate the new velocity. Or you can sit there and go, oh, I'm going to double it. That's underneath the radical. It's going to increase by the square root of 2. Okay? I don't care. Figure out what fits in your wheelhouse. Figure out what you feel most comfortable doing that analysis. But here's the cool thing. Derek, instead of doubling the distance, let's say I made it 4 times higher. If I made it 4 times higher using this method, what would I do to my velocity? Instead of that being a 2, I'm going to make that a 4. By how much? What's the square root of 4? So if I want to double my velocity, I'd have to increase my height by a factor of 4. If I wanted to go 3 times faster, what would I do to my height? If I wanted to triple, what would I do to my height? 9. I'd increase it by a factor of 9. Okay? See that? So it goes 1, 4, 9. Notice that those are squares. 1, 4, which is 2 squared. 9, 3 squared. Okay? You go to the next one, 25. Oh, that would increase it by a factor of 5. Okay. So let's talk about time. Okay? Let's talk about time. So in this situation, I'm going to double the height again. So that's going to be 2D over A. So if you follow that same thought process, Peyton, since that 2 is underneath the radical, if I double my height, what's going to happen to my time? It's not going to double. That 2 is underneath the radical. So what's going to happen to my time? It's going to increase by the, let me give you a hint, it rhymes with care root of 2. Perfect answer. Brilliant. Okay? Because if I pull that out, I can write that as the square root of 2 times 2D over A. So if I double it, my time is also going to increase by the square root of 2 because it's underneath the radical. So that's the beauty of looking at all these in terms of variables. Okay, oh, right, it's underneath the radical. I double it. There you go. Okay, now, we're going to go back to projectile motion. So now we're back to the part of the story. So I'm going to take, come back here. I am going to take that baseball, and I'm going to launch it with a horizontal velocity of 5 meters per second from a height of 2 meters above the ground. So instead of just dropping this ball like this, okay, now I'm going to take that ball and I'm going to throw it like this, okay? Whoa! Okay, that bounced much higher than it was supposed to. Thank you, Dirk. Okay? So, now we're back to projectile motion. I'm going to throw that ball horizontally at 5 meters per second, and I'm 2 meters above the ground. I want to figure out 3 things. I want to figure out how long it's going to be in the air. I want to find the vertical velocity when it lands, and then I want to calculate the speed when it lands. Okay? Now, when I'm talking about speed, all I'm talking about is like, imagine that you have like a little radar gun in the ground, and you're shooting that radar gun at that ball as it approaches you. And you're trying to figure out what's going to be the reading on that radar gun, which is going to be a combination of your horizontal and vertical velocities. Okay, so let's talk about time. How long is that ball going to be in the air? Do we have enough information to figure out how long the ball is going to be in the air?
Yeah.
Yes. What do we need to calculate how long the ball is going to be in the air? Oh, time equals the square root of 2d over g. The fact that I threw it, does that have any bearing at all on how long that ball is going to be in the air? Tyler. I'm going to throw that ball horizontally. So here's my question. Tyler, I'm going to throw one ball horizontally at 5 meters per second. At the exact same time, I'm going to drop a ball and it's going to fall straight down. Okay? Which one's going to hit the ground first, or is it going to be the same?
It's the same.
Why? Your answer is right, but why are you right?
Because, well, that's dependent on vertical, like you're not applying a vertical force.
Fantastic. What happens in the X, or what happens in the X, stays in the X. What happens in the Y, stays in the Y. So whether I drop that ball or I throw it horizontally, the gravity mafia can only influence vertical motion. The fact that I threw that ball horizontally, not part of the story. In terms of time, in terms of my vertical velocity when it lands. So as this ball falls at certain points, if you could do like a slow motion video, you would see this ball that shot out at the exact same positions at the exact same times. They would be like mirror images of each other as they fell. They would land at the exact same time. They're going to land with the exact same vertical velocity. Everything's going to stay the same. Okay? Because the gravity mafia can't influence horizontal motion. So when you go to calculate this time, it's still 2 times negative 2 meters divided by negative 9.8 meters per second squared, and you're still going to get that exact same time of whatever that is, 0.639 seconds. That's still going to be 0.639 seconds. Nothing is going to change because the gravity mafia can't influence horizontal motion. So whether I drop this ball or I shoot it out, they're both going to land at the exact same time. Okay? No change, because it goes back to something that Tyler said. There's no vertical forces because I'm just going to drop it. Okay? Yeah. Is there horizontal motion? Yeah. Guess what? Doesn't matter. All right. Now, so we got that. Now we need to find the vertical component, and this is what we have to begin to keep track of. So when this ball lands, it's going to have a horizontal velocity of 5 meters per second. So this is just as this ball is coming in contact with the ground. Okay, just right before it hits. Because my Vx is going to stay the same. Because whatever happens in the X stays in the X. Gravity Mafia doesn't change the horizontal velocity. That's just 5 meters per second. Now, we already found the vertical velocity. We said that was 6.26 meters per second. We have that number. We've already found it. And it's the exact same. So when it lands, it has a vertical component of 6.26 meters per second, which is the exact same as if I just drop it, because the only thing that's being affected is vertical motion, because what happens in the X stays in the X, and what happens in the Y stays in the Y. Okay? So now I've got my vertical, and I have my horizontal. So to get my speed, okay, when projectile motion, when you're talking about speed, you're talking about the resultant of your X and Y velocities. So this is going to take somebody get a little calculator action going on. So I got Vx, which is 5 meters per second, and this goes back to vectors. So from the end of this, I'm going to draw 6.26 meters per second. And then I'm going to have that resultant. So again, this is just trig functions, okay? It's Pythagorean theorem. Y'all have done this, okay? We're just repackaging it. Oh, 5 squared plus 6.26 squared. So somebody get me that value. So 25 plus 6.26 squared. And square root of that. Should be around 8 or 9 maybe.
8.01.
Oh, not bad. Okay, so the 8.01 meters per second is the speed. So what that means is that imagine that you're in the ground and you've got a little radar gun and you're keeping track of the speed of that ball as it lands. Because the radar gun can't differentiate between X and Y components. The only thing it can keep track of is the resultant. Okay? So what that means is this. Is that when, let me start over. Need a little bit more room. Oh, come on, seriously? Is that when that ball is launched like this, the speed that you have initially is just going to be 5 meters per second because it doesn't have any vertical component to it. So as it flies through the air with the greatest of ease, that number isn't going to change. Because what happens in the X stays in the X, that number is going to stay constant as it falls through the air. Now, Miss Elliott, am I going to have vertical acceleration? Is my velocity going to change in the vertical direction? Huh?
It won't change for the last
No. I'm not asking, no, I'm talking about acceleration.
Oh.
Is my velocity going to change as it falls through the air?
Yes.
Yes, because it accelerates, right? Because the only force acting on it is gravity, which is acting straight down. So at this point, you're going to have a little bit of Vy, and the farther it falls, the bigger Vy becomes. So what that means is that as it falls, that resultant vector, there's two things that happen to that resultant vector. It gets bigger because you're getting a bigger and bigger Vy, and it gets pointed more towards the vertical because your Vy is getting bigger. As that Vy gets bigger, it's going to drag that overall vector down. So as it falls through the air, your speed would go something like this, where it's going to fall and it's going to turn downward like this. But your Vx is going to stay the same because the only acceleration vectors are going to be vertical because the only force acting on the system is what Tyler said. The only force acting on the system is going to be vertical. Now, here's the last question. I won't do this for obvious reasons, but I'm going to take Hank. I'm not going to do this, but imagine this. Imagine that I'm going to throw Hank at 5 meters per second horizontal at 2 meters above the ground. Okay? So imagine I have Hank 2 meters above the ground. I'm going to throw him at 5 meters per second. I'm going to take the baseball, and I'm going to throw the baseball at 5 meters per second from 2 meters above the ground. So imagine, if you will, you have Hank and you have the baseball. And they're both 2 meters above the ground, and they're both going to be launched at Vx, at 5 meters per second. Adana, which one's going to hit the ground first? Hank or the baseball, or will it be a tie?
Tie.
Why?
'Cause
You say that with no confidence, but you're right. It's going to be a tie. Why?
The acceleration is the same for both of them.
Fantastic. Where did I plug the mass of the object into the equation? Never did. Okay? Never did. Is there more force acting on Hank? Yes. Is it going to be harder to throw Hank? Yes. But once it leaves my hand, the only force acting on it is gravity. They're both going to have the exact same acceleration. They're both going to land at the exact same time. They're going to land with the exact same speed. Now, there's only one calculation we have left to do. And that's we need to figure out how far they're going to go. So, range equals Vx time. So for both of those, that's going to be 5 meters per second. And our time, what was our time? What was our time? 0.639. So Izzy, do us a favor. Take 5 meters per second times 0.639 seconds.
3.20.
3.2 meters. So they're both going to travel 3.20 meters because that's how long they're in the air, and that's that Vx. Now, here's an interesting thing. If you were to draw a velocity versus time graph, that would just be a horizontal line at 5 meters per second at 0.639 seconds. Okay, that's what that would look like. Vx, boom, there you go. Okay? Now, but if you were to draw a vertical velocity versus time graph, that would start at 0 meters per second, and then that would have a downward slope of negative 9.8 meters per second squared. And again, this is the big picture, okay? This is the big picture. Oh, right. Hey, I'm accelerating in the vertical direction. The only way I can accelerate in the vertical direction is if my net force does not equal 0. Oh, my net force doesn't equal 0 because gravity is the only force acting on it. Okay? And the fact that it's moving horizontally or if it's dropped doesn't matter. Because what happens in the y stays in the y. What happens in the x stays in the x. Gravity can only influence vertical motion. We assume that there's no horizontal mafia, so whether I drop that ball or if I throw it, it's going to have the exact same vertical velocity time graph because the only influence is gravity. Got it? Good? Grand. Okay, stop that for a second. This lab. So you're going to take yonder ramp like this, and you're going to take a C-clamp, because it looks like a C, and you're going to clamp that to the edge of the table like so. If I can never get it up there. Come on. Here we go. So you got a ramp. Here's your table. Here's going to be the ramp. Boom. And then you're going to take a small marble like this, and you're going to hold it up on the ramp like this, and you're going to let go of it. Now, later on, we're going to talk about energy. So we're going to talk initially about energy. So you have two types of energy. You have kinetic energy and you have potential energy. So what you're going to do is you're going to lift it up, and you're going to give that ball a certain amount of potential energy. Mother Nature doesn't like potential energy, okay? Somebody said something back and forth between potential energy and Mother Nature, Snapchat, Instagram, Twitter, I don't care. Somebody said something, and Mother Nature and potential energy don't like each other. They never have. They've held a grudge since the beginning of the universe, okay? Mother Nature and kinetic energy, they're tight, okay? They're besties, okay? They are in the private chats, okay? They like each other. Potential energy, not so much, okay? Outside looking in. So when you hold this up here, you have potential energy. Mother Nature goes, I like kinetic energy because we're besties. So when you let go of it, oddly enough, it begins to roll down the ramp, and then oddly enough, it turns into a projectile, okay? So what we're gonna do is we're gonna analyze this thing from the moment that it leaves the ramp. Don't worry about the ramp part of it, not part of the story. We're just using the ramp to build up velocity. That's all we're using it for. Thank you, Dirk. Okay? So ramp, not part of the story. Potential energy changes into kinetic. So what you're going to do is that you are going to roll the ball down, get an idea of where it's going to land. Once you get an idea of where it's going to land, then you need to take a piece of paper and you're going to lay that down where you think it's going to land. Then you need to take a piece of carbon paper like this, okay? Put the diamond side up. We're going to use this throughout the a couple different times. And then when the ball lands, what happens is that transfers a mark onto the paper. So it used to be carbon paper was used all the time. And we still use that vernacular even in emails. So CC stands for carbon copy. So how back in the dark ages, like when I was your age, you didn't have computers, you had typewriters, okay? And so what would happen if I wanted to type the word physics, P-H-Y-S-I-C-S, okay? And I would have a piece of paper there, and it was live. If I typed the letter P, the typewriter would manually strike the paper with the letter P, and that would get transferred from a ribbon and the ink onto the paper. So it was a mechanical process, okay? And there was no spell check, there was nothing. Like, if I wanted to spell P-H-Y-S-I-C-S, and if you screwed up, okay, there was no backspace. Oh, I'll just delete that, okay? Like, because once it hit, if I spelled it P-H-Z-I-K-S, it's like, oh man, I hit the wrong letter, okay? So you'd have to like white it out or do something to get rid of it. Because number one, there was no spell check. Number two, you'd have to like physically get rid of that. So what happened is, let's say I was writing a letter of recommendation for Izzy. Izzy says, hey, Mr. Burkamp, I'm applying for an FFA scholarship. Can you write me a letter of recommendation? Sure. Okay. So if I wanted a copy of that, and again, this is before copying machines were even readily available. This is dark ages. Dark. Dinosaurs had just become extinct. It's that long ago. And so what would happen is that if I wanted a copy of it, so I would send the original to the organization, but I would want a copy of that letter, okay? There was no capacity to store it digitally or anything. So what I would do is that I would have a piece of paper that I'm going to type on. So this would be the original copy. Then I would put a piece of carbon paper like this, and then I would have another sheet of paper back behind it. So that way when I type the letter P, and that would come up and it would strike the letter on the original, then it would transfer that image from the carbon paper to the back side. So I would have a carbon copy of it. So when you do email, that's what that CC stands for, because it's a throwback to the old days of writing letters. So I would, and at the bottom, so that I would have to put, well, kind of morally, when I wrote that letter, at the bottom I would put CC, Stan Burkamp. So that way the people that knew that were getting the letter knew that I kept a carbon copy of it, okay? So that they would know, okay, hey, I've got the original, but Stan Burkamp, who wrote the letter, has a carbon copy of it. And so you might have like maybe two, or like if I wanted Izzy to have a copy of it as well, then I would put a third piece of paper, okay? And then I would put CC, Stan Burkamp, Izzy, so that the people would know that they're getting the original, I'm getting a copy, and Izzy is getting a copy of it. So everybody would know, okay, who's going to end up with it. So when you do email, that's what that CC stands for. Okay, little historical lesson on communication. Okay, so here's what you're going to do. In terms of data, you're going to set up the ramp like this. You're going to measure the height of the table. You're going to measure from the top of this ramp here down to the ground. Boom, there's your height. Okay? Then you're going to measure the range. You're going to measure from the edge of this. You're going to transfer that line down out to that piece of paper where that mark is. That's going to be the range. That's all the data that you need. You need height and you need range. Don't ask me for a stopwatch. You're going to calculate the time. Okay? You're going to calculate all these different velocities. The only data that you need is range, time. Now, why do I not have a line from the mass of the marble? Why don't you need the mass of the marble?
Because acceleration and distance are like the only thing
Yeah.
that affect it.
In all the equations, guess what? What variable do you not need? Mass. That's why you don't need it. So you don't need the mass of the marble because it's not part of the equation. Okay? Just like, hey, Mr. Burkamp, what's the temperature in the room? I don't have a line to record the temperature in the room because it's not part of the story. Okay? How much did it rain last night? Oh, about a half an inch. Guess what? Not part of the story. So the only thing that's going to determine all of these are two things. How far it falls, distance, and the gravitational acceleration. And you can do everything else from that. Now, on your calculations, everybody's is going to be different. You're going to calculate time. Okay? You're not going to measure it, you're going to calculate time. That time is going to come from 2D over G. You're going to know how far it falls. You're going to know the gravitational acceleration. That's what's going to allow you to calculate time. Then from that, you're going to know range. So you know range equals Vx time. So once you get that time, and you're going to know the range, you know how far it goes, that's going to allow you to determine Vx. Vy, yo. That's your initial vertical velocity. Do not make this difficult. What's your initial vertical velocity? 0. You're rolling it off a horizontal ramp. Okay, so Vy0 is just 0. Then you need to find the final vertical velocity. Okay, and again, that's the same whether it's dropped or whether it rolls off that ramp. You're going to find Vy, just like I did in the examples. Now, down here where I have V resultant, this is what I want on that V resultant line. You're going to come in here and you're going to know your Vx, and then you're going to know your final vertical velocity, and then you're going to find that resultant, okay? So the resultant is the speed. So I want two things on that V resultant. I want this, the actual magnitude, and then I want this angle right in here. Okay? Don't worry about subtracting it from 360. Just give me that angle in there. And that's typically, this is an ish, it's typically around 70 to 80 degrees. Okay? Somewhere in that ballpark. Okay? So I want this angle, use a little inverse trig action. You got Vy, you got Vx, and then that resultant. That is not range. That is the resultant of those two velocities. Okay? So then you got a bunch of questions to answer. When you get to question 1 on the back, yes, there is a backside. Car is going at 112 kilometers per hour, drives off a cliff. It's a lemming problem. You're going to go driving off of a cliff. What are you going to have to do with 112 kilometers per hour? Convert it to meters per second. 112, how many significant digits does that have? 3. Peyton, how many significant digits am I going to have in that velocity?
3.
You're not going to round, are you?
No.
Thank you very much. Okay? Now, so you can do all these calculations. Now, when you get down to this next section, I'm going to say if the horizontal velocity was doubled, so in other words, the car is going to go twice as fast. It's going to go 224 kilometers per hour. I want to know how would each of the following change? Time, range, vertical velocity when it lands. So there's a couple of ways you can do this. You can do smash mouth physics, and you can go back through and you can recalculate all the values and write them down. Okay, so if you're into calculus, like Burkamp, I hate variables, it flips me, oh, I hate them. I want numbers. I have a calculator and it's really cool and I know how to use it. Good for you. Go through and recalculate the numbers. Okay? Or you can just look at the variables and go, oh, it's going to double. It's going to increase by the square root of pi. It's going to, whatever it's going to do. Okay? So what you cannot do is just not say, oh, it's going to change. Oh, it's going to be different. Oh, it's going to increase. Okay? No. If it changes, you either tell me by what factor it changes, doubles, triples, increases by the square root of 5, whatever it is, or you actually calculate the values, okay? I don't care. But what you cannot say, it's different or it increases. I want the actual numeric values. And you can either calculate them or you can tell me how much it's going to change. All right, I'm done, Ron. I'm done. You're on your own. Go be free.